So for this assignment, we used Octave for both the NFET and the PFET. And here's what our graphs look like. So for the thermal voltage, we were able to calculate this by looking at the source sweep. We just took the gradient along this linear region here, because if you're holding the drain and the gate voltage constant, then the slope of this linear region is going to be -1 over the thermal voltage. So we were able to extract that parameter. From the drain sweep, once the device is in saturation, which is about 100 or 4 times the thermal voltage, about 100 millivolts, the sigma is just the value of this gradient here, and we found this to be really, really small, so all we had to do is do polyfit on that. For kappa, this is the drain sweep, so kappa is the parameter here divided by the thermal voltage, because when you're holding both the drain and the source constant, the change of this linear region is kappa divided by the thermal voltage. So we just take the parameter from here. For I naught, we're able to calculate this value just by looking at the value here when the gate voltage is equal to 0, because when the gate voltage is equal to 0, then our entire expression in the exponent is equal to 0, and then whatever the current is just going to be equal to I naught. For the threshold voltage, once again we used a log plot on the gate sweep, and we did 2 things. So we took a linear fit of this linear region here for these points, about 20 to 0.2 to 0.5 or so, and we did a quadratic fit from 0.5 to I think about 0.8, and then we just did we just set them equal to each other and solved. And so our values for the NFET was 0.0286 volts for thermal voltage, 2 times 10 to the -11 for sigma. Kappa was 0.633 volts. I naught was 1.81 times 10 to the -10, and the threshold current was 4.39 times 10 to the -5, and the threshold voltage was 0.561, and they're all what we expected. So for completeness, I'm just going to show the PFET script as well. So most of these curves are just the opposite as we'd expect, and for all these curve fits, we just did the same exact thing we did for the NMOS, where for thermal voltage we found the gradient of this linear curve. Sigma, same thing. Kappa, same thing. For I naught, instead of taking the voltage here, we took at 0, we took the voltage at 2.4, and for the threshold voltage, we did the same exact thing where we did the quadratic fit and the linear fit, set them equal to each other, and to get the right value. And these were the values we got for the PFET transistor. So the next thing we did was we plugged the parameters we took from the static experimental data, and we plugged it into our NMOS transistor simulation model. And our data looks pretty similar to what we got for the gate sweep, because this is a gate sweep. Yep, it looks very similar to what we got previously. So then we did pretty much the same thing, except for a sweep of the drain. And once again, we get a very similar plot. So instead of having the gate connected to this ramp, we just kind of connected the drain to its own ramp. And yep, same results as the static experimental data. And the last plot we did was we set up the source sweep. So once again, the gate we set to 0. This voltage source here is actually 0 volts. And we set the drain back to 2.4 volts, and the source was just set to this voltage sweep. And our data looks similar to the experimental data that we
where we extracted the parameters from.
So the last thing I have to show is the remote and local data can be collected from the remote and local FPAA. So, well, here was the circuit we used. We used an ARB-Gen, which is digital to analog converter, and then the measure voltage, which is an analog to digital converter. And so we got these two sets of data. The left is the local data, and the right is the remote data, which Dr. Dora had to send to us because at the time the remote FPA wasn't working. So I assume that column A is time, column B is voltage in, and column C is voltage out, and then this data over here is all voltage out. So that's what this plot is here. The blue line is just a reference voltage where V in is equal to V out, and the green line is our the local voltage out, and it looks pretty good for this conversion. However, the remote data does not look so good, where in the 10th point, where if the voltage in is 2 volts, it's about half. It's half of the voltage in, so it's not a very effective ADC DAC conversion.